Good morning. I would like to thank the organizers for this opportunity and congrats for this great event. It's been very nice to be here in person. So this is a joint work with Carlili there and Vinicius. Vinicius is a former PhD student of ours. So it's nice to present part of his work. So I'll talk about geometric algebra and distance matrices. This is not actually a bibliography, it's just a guide. The main idea was to reformulate the results presented in this first reference. This is based on linear algebra. And we want to use the conformal geometric algebra to describe the same problem and use some strategies presented in this second reference. So this is an outline of the presentation. I'll start with some basic definitions and some fundamental results on distance matrices. Then I'll present the linear algebra approach, this original approach of that first reference. And then the new approach using CGA. And finally, I comment something about the ongoing works and future works. Okay, so the first definition is the Euclidean distance matrix, or an EDM for short. We say that a matrix will be an EDM if we can find a sequence of points or a set of points where the square distance between each pair of points are satisfied by the entries of a matrix. So necessarily this matrix must be symmetric and hollow with it has no diagonal. And all the entries are non-negative numbers. So we want to find sufficient conditions for a matrix to be an EDM, also provide a solution or a realization for this matrix in the space of minimal dimension possible. So about the number of solutions. Okay. The first result is about the number of solutions. If a matrix is an EDM, or if we can find a solution for a matrix, we can find infinitely many others. This is possible, for instance, because we can rotate or reflect or translate the set of points. So these transformations are isometric. And also we can add no coordinates in each vector, in the define of each vector. So in this case, we are only increasing the dimension of the space where the solution lies. And this is important for the method we are going to describe. So, and talking about the dimension, the next important definition is the embedding dimension of an EDM. This number, we want to find the solution with the minimum dimension, in the space with the minimum dimension possible. This number we call the embedding dimension of the matrix. It has an upper bound, so it will be for an n times n matrix. It will be at most n minus 1. And okay, so we will state a theorem that will give these results we are searching for. But before we have these two lemmas, the second lemma is purely technical, but the first one is very important for the method. It could be even more general than we have here. But if we have a submatrix with embedded dimension k, the next submatrix will have embedded dimension either k or k plus 1. So we will construct the solution working with the submatrix. So it's important to use this result. So this is the theorem that provides these results in this linear algebra formulation. So if we have symmetric hollow matrix with all non-negative entries, This matrix will be an EDM with embedded dimension K if and only if we can find a set of points with this structure. So the first idea to apply conformal geometric algebra to this problem was to write this theorem in a easier form, or okay, at least giving some geometric meaning for these points. At least for me, it's not so easy to see the kind of solution this structure have. So, but it's something like this. So the first point will be in the origin, and the next one we increasing some coordinates. So in general, we have this kind of solution. So to prove this theorem, we won't prove this theorem here, just to give an idea of the procedure. But the idea is to construct this solution based on realizations on each submatrix. So again, given a symmetric column matrix, we define the submatrices. And for the first submatrix of dimension 2, we always have this solution. So the first point is 0. The second point is the square root of A12. And then what we do to find the next point is to add a no coordinate in each vector. So now they are in the two-dimensional space, and we look for x3. If we have no solution for x3, we can stop the process. The matrix will not be an EDM. Otherwise, if the second coordinate is also 0, we can get rid of the zeros, the second coordinates, and our solution will still be in the one-dimensional space. So the embedding dimension in this case remains unchanged. It remains 1 for this point. Otherwise, we have two possible solutions, and we pick one of them. So this is repeated until the last submatrix. And to find x3 based on the linear algebra approach, what we do is to solve nonlinear systems. So for x3, we have this situation. The first point is in the origin, so we can transform this system, this nonlinear system, into in this case, just a linear equation for the first coordinate of x3. And if we have a unique solution for this coordinate, we can search for the second one. And we have those possibilities we described it before. So if this square number is negative, we have no solution, we stop the process. And okay, if the second coordinate is 0, again, the embedded dimension will be still in 1. Otherwise, we choose a solution. So far, we have no criteria to pick a solution, so we choose one and follow the search. So the last step, in general, we'll have a solution, a partial solution like this. And if the embedded dimension of an-1, the last submatrix, equals to k, we have this partial solution. We add a no coordinate in each vector in trying to find xn. Now we have a much bigger nonlinear system, but again, we can transform it to a linear system for the first k coordinates. And if we have a unique solution for this first k coordinates, A is not an EDM yet. Okay, it can be an EDM. If we have no solution, A will be not an EDM, and then we can find the last coordinate. We have these possible situations. If this square number is negative, A will be not an EDM. Otherwise, we decide if we increase or not the embedded dimension, and we have a solution for the matrix. So this is the linear algebra approach. So we are able to recognize an EDM, also give a solution, and also find the embedded dimension. And the idea is to give another formulation for the theorem using CGA, and actually replace that nonlinear system in a straightforward way using sphere intersections. So we use this result. So the idea, the main idea for our procedure is to have this number n and the number k the same. So we have a sphere intersection which will be either an empty set, a single point, or in our case, a point pair. What we call one sphere here is a point pair. So we define the spheres in CGA like this vector Si, and we perform the intersection using the outer product. So we can see if we have an intersection or a real intersection or not with this parameter t. Otherwise, you can simply compute center and radius of rounding objects. This is well-known formulas. And we see the sign of the squared radius. So if it's negative, we don't have a real intersection. Okay, so this is the same slide we saw before. The beginning of the solution is the same. We will work again with submatrix. For the first one, we have the solution. The first point is 0. The second one is like this. We add a null coordinate in each vector. And now to find x3, instead of solve a nonlinear system, we search for sphere intersections, in this case, intersection of two circles. And okay, x3 will be in the intersection of spheres centered in the previous points with the squared radius given by the corresponding entries of the matrix. So at some point, we will have like a submatrix A m minus 1 with embedded dimension k. We do the same, and then xm will be an intersection of m minus 1 spheres centered in the previous points with squared radius given by the matrix entries. So we can state the theorem using CGA. It's the same. We have a symmetric hollow matrix. This matrix will be an EDM with embedded dimension k. If we can find a set of points with this structure, but now we have geometric meaning for each point. We know the first one will be in the origin. All the other ones will be in sphere intersections. So this is actually an alternative way to extract a point pair of sphere intersections. So if we have an embedded dimension k for this submatrix A m minus 1, we add no coordinates in each of the m minus 1 centers, previous centers. So they will be in a hyperplane of this k plus 1 dimensional space. So the center will be in this hyperplane. The center of the intersection will be in this hyperplane. So this hyperplane is orthogonal to this extra dimension. So it's not the center of the intersection that is orthogonal. The hyperplane is orthogonal to ek plus 1. And then we can compute the radius. If it's 0, the intersection is exactly the center, so we don't have to increase the embedded dimension. Otherwise, if we have a point pair, this will be in the center plus or minus the radius times this dimension. Okay, so if you have a point pair, the center will be exactly the center of the point pair, and you go up or down to decide xm. Okay, so this is an example, a small example of 4x4 matrix, and we want to see if it is an EDM and find a solution in minimal dimensional space. So we start from A2, the first submatrix. We have this partial solution, x1, x2. So the embedded dimension so far is 1. We increase the dimension of space. Here it's important to notice that A13 and A23 need not to be squared. They are already the square radius of the spheres. So it's fine. And then we perform the outer product of S1 and S2. And okay, we find that the center of this intersection is in the origin. The square radius is positive. So we have to increase the dimension. The second coordinate of X3 is non-zero. So we just pick one. We have no means to decide which one is better. So I picked the positive one. So we have this partial solution in a two-dimensional space. This is a realization for the 3x3 submatrix. Then we do the same. We add a no coordinate for each of these three vectors, and we perform a three spheres intersection using the outer product. Again, we compute the center, we compute the square radius. In this case, the square radius is 0. So the last coordinate, the third coordinate of X4 will be 0. We can get rid of this last coordinate. So our solution is still in a two-dimensional space. So the embedded dimension of A4 is still 2, which is the embedded dimension of the matrix. So then we have a solution for this 4x4 matrix in R2. Okay, this is an outline for this method, but it's what we made here. With each step, we compute the radius, we see the sign of the square radius, and we decide if we increase or not the embedded dimension. So we use only precise data here. So what we are doing now, what Vinicius is trying to do, is dealing with imprecise data in the matrix entries. The procedure seems to be very similar, just adding spherical shells in the intersections. This may be perhaps an advantage of this approach, since for linear algebra, the procedure is not, apparently is not so straightforward, generalized. And for future work, so we want to work with missing data and apply to problems related to dimensionality reduction, multidimensional scaling, something like that. And okay, that's it. Thank you.